PSA, data book. Okay, look at this one. Molecular weight of 19 or 15.95 or specific gravity of 0.55. Natural gas methane. Okay. PC is what? Jason? Oh, okay. Next to you. What's your name?
Claire.
Claire. I'm sorry that you sit next to Jason, but what is PC? Who teach you that class? You are going to bring out the house again, or what? What's PC? Critical something? Critical pressure. And that is critical temperature. We don't use it, okay? But that is used to calculate the reduced temperature. But we are lucky. This chart doesn't plot as reduced temperature and reduced pressure. We have just pressure and temperature. Okay, in Fahrenheit. 1000, 0 Fahrenheit, 25, 50, 75, 100, blah, 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 blah. Then we can calculate Z factor. And you don't need example for this because you used it before, right? You know pressure, you know temperature, then you can calculate Z. Z, it's kind of 1, or maybe 0.8, 0.9 or something. Just that. Use this chart. But before we can use the chart, we need to know what is the molecular weight. So this chart is for gamma equal to 0.55. Next one is for 0.6. Next one is for 0.65, 0.7, 0.8, 0.9. How do we get molecular weight of the gas or average molecular weight of the gas? If the gas is just single component, we know it right away, right? But it can be many components. For the case of many component, okay, Rohan, yes. What do we do? How do we get average molecular weight?
We get the average molecular weight based off of the concentration, like concentration multiplied by molecular weight.
Concentration, mole fraction,
Yeah,
weight mole fraction. Who teach you that? This other department.
We learned it on top.
Oh, okay. So Dr. House did a good job, right? I think so. We use this. Since he can answer it, okay, let's review this quickly. Summation of total mass is mass 1 plus mass 2 plus blah 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 blah. PV equal to Z, mass over molecular weight multiplied by RT. So mass over molecular weight is N, is mole, right? So mass is PV equal to ZRT multiplied by molecular weight. Put this thing over there. Then we have summation of mass equal to summation of all this. And of course, we can say, hey, mathematically, mass is molecular weight multiplied by PV over ZRT. So this whole thing should equal to total pressure, total volume divided by ZRT multiplied by molecular weight, average molecular weight. Move this part to this side, this part to this side, rearrange it, we see that molecular weight is based on, is a weighted average based on volume or volume fraction. If we know volume fraction, then we can get average molecular weight. Okay? So when we know percent by volume multiplied by molecular weight, 1% by volume multiplied by molecular weight, 2 add them together divided by 100, then we get average molecular weight. Good. Once we get average molecular weight, then we know which chart to open, then we know what is Z factor. After we know the Z factor, we put it back over there, then we know the density. After we know the density, we put it back over there, then we know V sub E. You expect it to be like 50, 60 or something. If you get erosional velocity of 0.1 feet per second, I think something wrong. Or you get 300 feet per second, there's something wrong. It typically is like 60 to 70. If you get far away from this, too far away, you may want to double check your answer in the exam. Okay? So we're done with the average molecular weight. Good. And this one is just air. What is molecular weight of air? I have mole percent. Oh, by the way, mole percent and volume percent, or mole fraction and volume fraction, they're the same. Identical. Exactly the same. So you can use one another. The reason that I say that it is the same is based on the derivation. And review it for yourself. But it's just the same. Okay? Next, you need to know, okay, this slide, review by yourself. How do we calculate average molecular weight of air? So I know mole fraction of each, then I get it. We need to know how to convert between mass fraction or percent by mass and percent by volume and percent by mole. This table shows when we have percent by mass, I do 20 divided by 32, I get that many mole. That is for oxygen. For nitrogen, I do 70 divided by 20. So I try to get mole percent based on mass percent of air composition. Okay. So when I get mass divided by molecular weight of each, I add them together. Then percent mole, the way that I get 9.09 is that divided by that multiplied by 100. I use that formula. It was an exam 2 years ago. Okay, so that you know which chart to open. The average molecular weight. After we get the average molecular weight, we divide it by 29. Or you can do 28.8 something or 28.9. So that we know specific gravity. Once we know if we don't know specific gravity, we cannot do several things. Look at this one, this chart. How do you know whether you use this chart or that chart? One of them is 0.6, one of them is 0.7. So we need to know how to get it. So in the exam, for example, I give you the gas composition, just mole percent. Then you have to calculate average molecular weight divided by 29, get specific gravity, and then know what chart to use. Of course, if you use the wrong chart, everything that you did is just wrong. And if everything is wrong, how much do you think you should get? 0, right? If everything is wrong, it's just 0. I'm sorry. So be careful. Okay, we're done with average molecular weight. And it is important. Erosional velocity. If I substitute the formula, that formula into here, instead of rho g, I put the whole thing in, take the square root or something, I can rearrange it and get a new formula. V equal to 0.6 c square root t over ps. We talked about this already. Typical value. That or V erosion, whichever is less. Okay. We may need to consider the pipe material. If it is compatible for water, or do we have multiphase for the corrosion issue? CO2. So that erosional velocity. We know at what point erosion will happen. Next step, we need to know how fast that gas is flowing in a pipe. If I have 10 million standard cubic foot per day, does that exceed the erosional velocity or it doesn't? I don't know until I use this formula. This formula basically is a volumetric flow rate divided by cross-section area. Just that. But it does some kind of conversion. Okay? Q is MMSCFD. That's Q. T is the temperature, in situ temperature. Z is the compressibility factor in situ at the in situ condition. D, pipe diameter, inner pipe diameter in inch. P is pressure. And here's the derivation of it. So it basically comes from Q over A and some unit conversion. And I skip, it doesn't mean that it's not going to be anywhere. It is important, so maybe just I don't know where to put, maybe quiz or something. LTX unit. This you can do it, right? It's like what 109.9. How do we get 109.9? And I show you once, and then you can do everything that is similar to this. Okay, let's do LTX unit. Okay. LTX unit is low temperature exchange. It can use to melt hydrate. It is for well producing high pressure gas along with light crude oil or condensate. LTX can stabilize fluid. What do I do? So separation at low temperature can get more liquid. So we can get more liquid with LTX. It is not very efficient stabilizer as coffee condensate stabilizer because absent of tray packing. So LTX doesn't have any packing, but it can give us a little more liquid. That's what it is. And additional recovery from LTX unit is small, normally small, and may not justify the cost operating complexity of LTX. LTX is not just more expensive, but it's a little more complicated to operate. The problem with the complication in the, like, if it's too difficult to operate, is that we have to train the person who operates this more. Train more means cost more. And also, if it is too difficult to do anything, what if they do a little mistake? Make it doesn't work. You don't like that, right? So when it's difficult to operate, this is what they think about. But it has some advantage. It can replace two things at a time, line heater and dehydrator. It remove water to be less than 7 pounds per mmSCF not D, per minute cubic foot. Yes, not D, I'm sorry. No D. If operate correctly. But if you don't operate correctly, you have too much water. So conventionally, we have line heater plus dehydrator. But for some case, it can be just LTX to replace those two. How does it work? Inlet gas stream is choked at the well to 2000 to 3000 psi until the temperature declines to about 120 F. This is above the hydrate formation temperature. Okay, so we show it first. Gas from the high pressure separator enter the coil in the bottom part of low temperature separator. What does that mean? Let's take a look at the picture. So we have this coming in 2000 to 3000 psi. We have a separator. Okay, we can take water out, condensate out, and then the temperature. This thing has high temperature, right? 120. So it's high enough. It go inside and then come out. So the heat of the high temperature gas stream can be used to melt any hydrate that is in the vessel. So high temperature gas stream, we have the temperature to, where's the choke? Let me go back a little bit. So number 2, gas from high pressure separator enter the coil at the bottom part of low temperature separator. After the coil, gas cool down to about 10 F above the hydrate temperature before entering the choke. Choke is inside the separator, so hydrate cannot plug the choke. Hydrate from the pressure drop. Hydrate form as a pressure drop across the choke. The hydrate fall into the bottom part of the low temperature separator and melt by heating oil. Okay, so the choke is here. The choke is inside this thing, right? When it go in here, it have the choke, the temperature drop, it have condensate and water come out, but we don't have hydrate because it's that's a choke. We don't have hydrate because the hot stream from LTX used to melt the hydrate. Is this accurate, Danny? You want to add something more? No? So choke is inside the separator, so hydrate cannot plug the choke. Good? good design, right? So we put choke inside the separator and hydrate that form. Hydrate that form will be melted by using hot gas stream. So we have a choke, but the choke is inside the tank and the heat from that. How complicated this is? So think about this. How do I know that it is 10F above hydrate temperature? Do you use a chart? Yes, I have to do some kind of calculation or something. How do I know, like, is this, what if the heat from the gas is not enough to melt the hydrate? Is it going to plug the choke? It could. So that's why it says here, it will be very good if we operate it correctly. Okay? And when you see this diagram, hey, we have high pressure gas, go here, go inside, come out, have some kind of heat exchanger, and there's a choke, and choke is actually inside the separator, the hydrated foam fall down, and everything condensate and go this way. This is LTX. Memorize this. Let's move on.
That's one of those instances where the theory looks simple, but to keep all that in balance and working properly is very difficult. You don't see many of those units in the field.
How many? Like one in the field?
No, they're just not a common, particularly around the.
Is it in Legoland? If I drive to Legoland, will I see any of this? None.
I doubt it.
He doubted. Okay. Yes, question.
So are you intentionally creating hydrates in this?
Yes, I do. And it's melted by use the high temperature gas stream. Hydrate. When it's under the choke, it is above the hydrate temperature, right? But when it go through the choke, the temperature drop, and we have hydrate. So hydrate in the gas, it is falling down, but because of heat from that thing, heat of itself used to melt it, so it doesn't plug.
You're using that to extract the green gas out of it. You're treating the gas. And so it's almost a different system than your line heater that you've been talking about where you want the gas dry at a glycol unit somewhere on down the line. So you're trying to do it all in one unit right there. And that makes the difference of why you're allowing that hydrated form where you still got a lot of heat. We haven't talked about what it takes to get that amount of heat in there to do all.
Hydrate form in the separator, and in the separator we have heating coil, and heat from the coil come from the gas stream, right? And because heat from the coil go to the hydrate, it melt the hydrate. Good. And then we have water at the bottom, condensated water, so we can remove water and prevent hydrate and choke at the same time. Seems to be very good, right? Okay, some difficulty that I can see from this. You see this part, heating coil. We said, hey, heat from the gas stream, we use it. It doesn't have additional heat source. It doesn't have fire tube, right? We use heat from the gas stream to melt the hydrate. Okay, how will any of that happen? This means we have a coil, and heat from the coil have to go from inside to outside. That has to do with U value, right? And heat, we have to use QA, T sub M, and U to know how much heat transfer. And with that heat transfer, it will melt the hydrate. How do we know how much hydrate will form? I don't know. So that's why it takes some time to adjust and make it operate at the optimum point. Okay, so that's why in Legoland it's not quite common. LTX is not as popular as they once were. The process is difficult to control. The set point is dependent on well flowing tubing pressure temperature. When pressure temperature change, the control have to be reset to ensure that the inlet is cold enough and the coil is hot enough. So with the life of the well, when temperature pressure change, we have to change this again. If coil is not hot enough, the life fraction in the liquid phase increase. If gas is not cold enough, more intermediate component will lose to gas stream or something. So basically, if we don't operate it correctly, we have the problem. That's what it is. In winter, cold liquid may plug the liquid outlet of the low temperature separator. We done with line heater and hydrate. Okay. So by now, if any in the exam or the quiz, I think it's too much to put in the quiz, you should be able to tell what is LTX. Is it more expensive or less expensive than the line heater? If operated correctly, LTX can be used to replace what? It can reduce amount of water to be less than what? Okay. And if you see this picture, what is this? Is this LTX? Okay. Okay, hydrate inhibitor. There are three types of hydrate inhibitor. Thermodynamic inhibitor change the Festival law. Okay. In the homework, I think when I have the Festival law and I have your operating point is over there. That point we call the point where it is thermodynamically stable for hydrate to form. Why do I have to say that long? Why don't I say at that point hydrate form? Can I say that? But I say it is thermodynamically stable for hydrate to form. It's a lot more work. The reason is when we go inside the phase envelope, it is not 100% sure that it will form, or it's not like it doesn't form immediately. It's not like bam, it's formed. It takes time. It may be 10 minutes. If I say, hey, hydrate form, does it mean that it formed right away? No. I can say that hydrate form, you can say that hydrate form, that's for short. But to be correct, technically you say it is thermodynamically stable for hydrate to form. Okay? It may take some time to reach the thermodynamic equilibrium, but at equilibrium, the hydrate form. For example, it can take 10 minutes for hydrate to form, even though the condition is preferable for hydrate to form. Good? Tolani, can you walk around and see that on each screen they are watching my lecture? How about that? And if not, you just raise your hand, okay? I trust all of you that you pay attention 100%, but I also check. Good? Okay, three types of hydrate inhibitor. We have thermodynamic inhibitor, kinetic inhibitor, anti-agglomerate. Anti-agglomerate is, this means it may form, but it doesn't get together. Okay? Thermodynamic inhibitor means it moves the phase envelope. Okay? So this means it may shift this line to be other line. That's what it is. So when we have temperature, pressure, thermodynamic inhibitor shift the line. Kinetic inhibitor slow it down, whether it's formed or not, to slow it down. Most common thermodynamic inhibitors are methanol and glycol, but by disrupting the thermodynamic equilibrium condition, the hydrate temperature is reduced. So it's changed the hydrate phase envelope. What are those? Okay. MEG. Monoethylene glycol. That's a hydrate inhibitor. Just tell them to turn it on and pay attention, okay? So MEG is hydrate inhibitor. Monoethylene glycol. It's a glycol. When we put it in, the hydrate doesn't form, or it have a hard time to form, or it needs a higher pressure or lower temperature to form. MEG we inject it to subsea 3. Let's talk about other type. LDHI, low dosage hydrate inhibitor. It is one type of kinetic hydrate inhibitor. It's a polymeric chemical. It's a polymer. Inhibit nucleation and crystal growth, but do not inhibit agglomeration of crystal once nucleation occurs. You remember hydrate is a crystal structure of water that traps gas inside, right? It have some kind of crystal structure. So kinetic inhibitor slow down or prohibit this crystal structure to form. But once it's formed, it may eventually form even if you have the inhibitor. That's what it says. Okay? Anti-coagulant inhibits the growth of the hydrate but does not stop nucleation. So anti-coagulant, we let it form, but it doesn't get together and it doesn't block the pipe. So these two, they are not quite promising. Why they are not quite promising? This one, we let it to form. Okay. LDHI, KHI, it form but slow, but once it's formed, it's there. So these two, it doesn't really completely prevent. To completely prevent, we have to disrupt the thermodynamic equilibrium or inject something. Monoethylene glycol, or we use methanol. Okay. What we can do is insulate the pipe. For onshore, you just bury the pipe and it's just fine. Or sometimes you may just insulate it a little. Hydrate is a big issue for deep water. For subsea pipeline, think about this. We have the platform, okay? And we have wellhead. So we have to move everything from the wellhead to the platform. So let's say this is a shallow water, okay? For deep water, you have kind of a chip, SPFO over here, and we still have the line connect. The distance over here, before it reaches the platform, it can be long. Long means 50 miles, 80 miles, that long, 80 miles. Very long, right? So to prevent hydrate, we can insulate the pipe, and we should insulate such that it have at least minimum hours time frame so that it doesn't have hydrate. For example, if we shut down the pipeline, we shut it down for 6 hours. Gas should be still hot. So insulation layer should be thick enough to prevent heat loss. It cannot prevent the heat loss forever, but for 6 hours, everything should be hot. Okay? But if more than 12 hours, it may be cold. We lost heat to the environment. Subsea temperature is about 40 Fahrenheit or 5 Celsius. Okay? That is subsea temperature. We can do methanol, but people don't quite like it on the platform because it have problem of safety. It is highly flammable, and how do we put a lot of that on the platform without worry that it will burn? Okay, we may have fire. So MEG is maybe a better choice, but methanol can be used, but we don't quite advise for methanol. Gas export pipeline. Gas export pipeline should have water content of 2.5 pound per million standard cubic foot. Less than 7, right? To have hydrate-free operation. So we may prevent hydrate by inject a little monoethylene glycol, MEG. MEG glycol can be recovered later. Okay, we can recover glycol. Methanol cannot be recovered cheaply. We need to do distillation. At minus 40 Celsius, methanol is preferred because glycol viscosity is too hot. So people use glycol in the plant, gas plant. Monoethylene glycol, diethylene glycol, and triethylene glycol can be used. All that prevent hydrate. Okay. MEG, low cost, low viscosity, low solubility in liquid hydrocarbon. Why is that matter? Solubility in hydrocarbon. What do you think? What?
It's not soluble, so it can be separated easily.
I think if it's soluble in liquid hydrocarbon, it doesn't do any good. That's what I think. And I will show you through Hammerschmidt calculation. Okay. Hammerschmidt equation It is just to tell how much do we need to add hydrate. Okay. Is it time's up? 2 more minutes. How much minutes tell us how much do we need to add hydrate, and that's the equation. And the parameter is given. Okay. And at the end we have K value. K value is a constant to use over there. And W is the weight percent of inhibitor. Okay, that's the weight percent. And we need to know molecular weight, right? So molecular weight is given here. C is 12, H is 1. Okay, and then you can calculate molecular weight. We need to know how much is methanol in vapor. If I just ask you to review all this, and then we are done and we can do separator, how about that? Oh no, we have to do this as the same as last time. Okay, for the short amount of time that we have left, let's do this. Just this slide. Delta T, depression of hydrate formation temperature. W is the weight percent, so this means if we add more, we can suppress temperature more. Just like that. Good? And more detail come later. And homework, I think homework can include this to some degree, because homework is due not next Tuesday but Tuesday after next. Alright? See you on what? Saturday. See you Saturday. Okay, thank you for coming.